Now, when we're speaking about molecular orbital theory, what we're doing is we're trying to make this fit with the theories in quantum just a little bit better than what they did with the SP hybrids. Okay, there's Lewis theory, there's orbital overlap theories, there's all these different types of theories. And molecular orbital theory is probably the best way to describe things, but it's unwieldy as far as how complex it can be. Okay, so we'll try to keep things basic, and I'm just going to show diatomic molecules in this case to show you how molecular orbital theory works. And it all works because it works with energy. Okay, so if I've got energy here, okay, that's an energy graph, low to high energy, so I'll draw this up here, okay. That's our first part, and what I'm going to do is I can select some atoms that are going to be bonded to each other. So I'm going to start easy here, I'm going to start with hydrogen, H2 gas, right? Okay, and if I do the Lewis dot structure of this thing, it's pretty simple to draw. H line H, okay? Nothing too complicated now. But now what we do is we look at this, and we've got to look at the atom on the left and the atom on the right, or the two atoms that are involved. So over here, I start with hydrogen 1, okay? And let me put it this way, hydrogen 1. And hydrogen 1 has a 1s orbital and has 1 electron. On the other side, so here's 1, here's 2. On the other side, I'm going to have H2, and it's got 1 electron and it's 1s orbital as well. Now, what's going to happen when those two things overlap? Okay? In order for this to occur, there has to be a lower energy involved when the two electrons start sharing. If it was higher energy, it wouldn't happen. So in order to get a bond, I've got to have lower energy. So what ends up happening is once these two things overlap, I'm going to get a bond between the two, the sigma bond, and it's going to be lower in energy. Now this is the universe, okay? So there's always a yin to a yang, okay? There's a Batman or a Superman, and there's a Bizarro Batman, or Bizarro Superman. There's a Bizarro Batman out there too. You know, he wears green clothes and he spends a lot of time at the YMCA. But if you've got, I don't know what that meant either. Okay. There's matter and there's antimatter. There's always an opposite there. Okay? And that's going to be what we call an anti-bonding orbital. So the one down here, this sigma bond, this one is the bonding orbital. And anytime there's a star there, this thing is the anti-bonding orbital. Right? Now, I can always find out how many bonds are between each of the atoms using something called bond order. And bond order is equal to the number of bonding electrons minus the number of antibond electrons. Is that still on the screen? Barely, okay? And then I divide that by 2, okay? And that'll give me my bond order. In this case with hydrogen, I've got 2 bonding electrons minus 0 antibonding electrons divided by 2, and I'm going to have 1 bond. And well, guess what? There's a single bond between the 2 hydrogens. Nothing we already knew, but molecular orbital theory helps confirm this particular idea, all right? So long as my bond order is not 0, I have a bond that exists. And that means I could have half a bond as well. What? Half a bond? What are you talking about, Dr. Wayne? Well, let's do something a little crazy. Because I'm a crazy kind of guy. And I'm going to change one of the atoms in hydrogen. H2 is going to be He. Okay? So in this case, instead of doing H1 and H2, I've got H1 or H over here and a helium. Now my helium has 2 electrons. The question is, does this particular bond work? Can this make sense? Is this molecular or legal by molecular orbital theory? I mean, we were looking at this, we're scratching our head going, what? Helium with an extra electron? That's bizarre. But is it really that bizarre? Okay? Now I've got 2 electrons here and 1 electron here. Can I do that? Can I put 3 electrons inside of an orbital? No. Okay? We've only going to put 2 electrons inside of an orbital. The spins can only be paired, so plus 1/2 and a minus 1/2 spin. The other electron has to go someplace else. What's the only place it can go to? That's right, up here. So what's the bond order of this weird thing? So now I've got 1 antibonding electron. So yes, I'll have 1/2. My bond order is a half, so this has half a bond. What does half a bond mean? I don't know, but that's what that means. Okay, I've got half a bond, means that it's legal. Okay, but it's probably unlikely. Anytime you get a half a bond, it's like a weird concept, right? Okay, it's like driving around half a car. It might work, but you've got half a car. It's not something that you're going to get a lot of places with because you've got half a car. So let's tweak this a little bit more. And I'm going to make this HE, HE. And will this exist? Notice you're all shouting at the computer like, no, of course it's not going to exist. You can't have HE too. Can you? There's a question mark. Well, let's look at it from molecular orbital theory. Put an extra electron in there. Now I've got 4 electrons I have to account for. Where are they going to go? Antibonding orbital. Now, if I have HE2, HE2, 2 minus 2 divided by 2 is 0, and this says, hey, you've done something illegal, you can't have a 0 bond, not going to work, sorry. Okay, well, that was easy. Let's wipe our hands and do that. No, we've got to do something else. And that something else just happens to be dilithium. Now, if you're a fan of Star Trek, you know you're always talking about dilithium crystals. Okay, you can make dilithium crystals, right? Yeah, Scotty, he's going to say, of course you can make dilithium crystals. I'm not powering this thing with craziness, you know. That's the best Scotty I can do. Get off my back. Okay. So I start down here, because lithium has a 1s, right? And on both sides it's 1s. So here's lithium, lithium, both sides of it. And the 1s we know is filled from lithium. Because if you remember the lithium's electron configuration, it's 1s2, 2s1. Okay? So I got my 1s that's filled. So I know from this that I am going to have a sigma here and a sigma star up here. So 2 electrons down here, 2 electrons up here. And does this make sense? Yes. Full inner shell. The inner shell is filled. If it's filled, you can't really do much with it, right? This is why the inner shells don't react, because they'll have a bond order of 0, because you're trying to bond with the antibonding electrons. It's not going to work. Okay? If I move up here, now I go to 2s. And my 2s now has 1 electron in each. And guess what? Same type of thing happens. I'll have an antibonding and a bonding orbital. Okay, so can lithium-2 exist? Yes, and what's going to be its bond order? Well, I've got 4 minus 2, that's 2 people, divided by 2, you get a bond order of 1. So what lithium-2 would look like is this. That kind of makes sense, right? Because that's kind of what hydrogen looked like. And both of them have 1 valence electron. Okay? But what about beryllium-2? Let's look at beryllium-2. Now for beryllium-2, now I get a little bit crazy. Well, not really that crazy. I just add an extra electron there. Now, is this going to exist? If you said no, good, go out and get yourself a cookie. Why? Because we've got the same number of antibonding electrons that we do bonding electrons. So this isn't going to work. Okay? Now some people are thinking, oh, well, if we go beyond beryllium, what are we going to get? We're going to get those p orbitals. And how does that work, Dr. Roy? Well, glad you asked. Let's work with carbon. All right, so here's carbon. All right? And what I'm just going to illustrate right now is just the 2s valence electrons, because we know the 1s are filled. So if I look at carbon's bond orders, okay, first thing we're going to look at is the lowest energy, because we've always got to follow energy. Okay, so we start filling in from the bottom. Fill in my electrons. Okay, so far, I have antibonding electrons and bonding electrons, both of which are equal. But now I've got these p electrons. So what do I start with first? And everybody says, well, the first thing you start with is sigma electrons, right? Wrong. Because what we start off with here is actually our pi electrons. Okay? And then the third orbital that's here is going to be our sigma. Okay? So then you're thinking, okay, well, then that means sigma is going to be the lowest, and then after that you got your pi the lowest, right? Well, no, of course not. Things can't be that easy. So if I'm looking at carbon, my first lowest up here is going to be pi, and I've drawn two little orbitals. So this is going to be pi star that starts off. Okay. Then up here, lastly, is going to be sigma star. Now this kind of makes sense because sigma star is the last bond, okay, the last single bond between the two. If that doesn't exist, nothing exists between the two. So we start filling in electrons. We start filling in those electrons, and you know what we get? We get 2 electrons filled in there, all right? So how many bonds exist between them? What's the bond order? 2, 4, 6. Minus 2 is 4, divided by 2. And what carbon should look like is this. Aha, almost. But anytime you have this kind of pairing, where you have antibonding and bonding electrons pairing up, there's a lone pair that has to be applied as well. So each one of these carbons has 2 electrons. Okay? The canceled electrons turn into lone pairs. And that's what we're seeing up here with carbon. All right? What if I went to nitrogen? N2. I'm going to keep carbon up here because why not? I've already got most of it drawn in. Sure enough, I get that. Okay? And that's what I end up seeing. That makes sense. 3 electrons, bond order is 3. I still have neutralized electrons here that turn into lone pairs. So that's what nitrogen looks like. Now, what about oxygen? Well, once you get to oxygen, something a little weird happens, and the sigma energy has to be lower than the pi energy as far as the bonding states go. So what I get here is a flip. All right? So once I hit oxygen and go to fluorine and follow that up with neon, I now go to a state that kind of makes a little bit more sense if you are a student of the hybridization theory. Okay? So here's sigma, and here's pi now. Now when I go to oxygen, okay, and go to O2, O2 now pairs an electron up here. All right? So I look at my carbon electrons, I fill in 2 electrons there, and I fill in 2 electrons up here, okay? So I've got 4 electrons. I've got the red pair from these where nitrogen was. And now with oxygen, I fill these electrons in, and I put them up here, which gives a nice property, okay? Anytime I have electrons that are unpaired, it means they're paramagnetic, which means that in a magnetic field, they're going to get trapped in the magnetic field and align those electrons to the magnetic field. It's what happens with iron. If you think about iron's electronic configuration, okay, iron looks like this, where you've got the 4s, and then you've got the 3d. Am I going off the screen? Not yet. Okay. So 1, 2, 3, 4, 5. Okay. 4s, 2 electrons there in the 4s, and then you go out 6. 1, 2, 3, 4, 5, and then you have a paired electron. What you get there with iron at that point is 4 unpaired electrons, which are susceptible to aligning in a magnetic field. That's why iron is magnetic. We make magnets out of iron. Stick your magnets to your fridge because it's made out of metal. Okay? If you don't have these paired electrons like you do with zinc, it's non-magnetic. And you're not going to get any alignment in a magnetic field. What this means is that oxygen aligns in a magnetic field when it's a liquid, or a solid in that case. So if you take liquid oxygen, it'll actually stick between a magnet. If it's a gas, it moves too fast to really stick to the magnet. Okay, so you can't choke people by holding a magnet up to them and saying, aha, I've aligned all of your oxygen. Not going to work. Sorry, supervillains everywhere. Okay. So now let's look at the bond order now with oxygen. Okay. So let's look at bond order of oxygen. Bond order of oxygen is going to be equal to the number of bonding electrons, 2, 4, 6, 8. So 8 bonding electrons minus 2, 4, divided by 2, and sure enough, we're going to get 2. So oxygen, as we all know, is a double bond. How many lone pairs are in each one of the oxygens? The lone pairs themselves are going to come from 2, 4, 6, 8. So I'm going to have 8 lone pairs. 1, 2, 3, 4. Okay, so there's 8 electrons there that are lone pair electrons. What's going to happen if I go to fluorine? Okay, this part we start filling these in, and that's fluorine. And when I get to neon, I fill those in, and that means neon can't form a diatomic molecule. So that's essentially what molecular orbital theory is all about. Okay?